and how to quantize the electromagnetic field. And I described some general points, and I also worked out a few differences very rapidly. So I want to go over them with slightly more detail today, and also discuss in more detail the concept of gauge dependence and gauge invariance which comes up in this. So the easiest, I don't want to spend too much time doing the algebra because the algebra is completely straightforward, so I will only stress the differences. So the easiest way to do this is to go back to what we did for the scalar field and make a comparison. So in the case of scalar field, we had a field operator phi, which we could write as integral, we wrote it as d omega k most of the time, but it is convenient here to actually expand it out. So we have d3k over 2 pi the whole cube and 1 over square root of 2 omega k. I will use that normalization. So that you have ordinary non-Lorentz invariant creation and annihilation operators, ak e to the minus ikx plus ak dagger e to the ikx, where kx of course is on shell. This is what we used to write as d omega k, and then there was the square root of 2 omega k which will be taken into this with capital A k. Remember the notation. This is what we did, and this was uptime after separating this phi into a bunch of harmonic oscillators. What we did was to start with the phi of t comma x, Fourier transform purely spatially, thereby identifying a set of functions of time qk of t which was complex. Then we said its real and imaginary parts will satisfy the harmonic oscillator equation, and then we know how to quantize a harmonic oscillator. You get 1 over square root of 2 omega a e to the minus I omega t plus a dagger e to the I omega t, and that is what we plugged in. So everything there will go through for electromagnetism. When we work in the gauge, which we call the radiation gauge, with divergence of A is equal to 0 and phi is equal to 0. So since phi is 0, we are only looking at the vectorial components for quantization, and even that is constrained by this. The corresponding expansion, corresponding to this for the case of a vector will be essentially the same. So let me just write it down and let us look at the differences. Suppose I look at A alpha. You will have this factor, and just for convenience I will use some notation like dk with an underline. So this whole thing is being denoted as dk with an underline over it. Okay, just for convenience of writing. Then we want to put things here. You will have a creation and annihilation operators, but we know that this is a vector, so there must be something carrying the vector index, which is called the polarization index or the polarization vector. So you have a E alpha, which will depend on k. It will also depend on what polarization we are looking at. So there is a summation over this lambda, which is 1 and 2. Then you will have a creation and annihilation operators A for each k and lambda, and you will have e to the minus ikx. Plus of course its Hermitian vertical to make the whole thing Hermitian. So let us stare at it and make sure we understand that, because this is the only difference. What is happening is that if I expand A as a harmonic oscillator, so you take A alpha and you expand it out, you will get integral d3k over 2 pi cubed q alpha, which is a vector, okay, or rather q alpha's component of t e to the I k dot x. So if I think of it as a vector, then this q is a vector. And eventually we want to have harmonic oscillate, the standard harmonic oscillators in terms of creation and annihilation operators. So you will have creation and annihilation operators for all the integers, alpha equals 1, 2, 3, right? However, there is a constraint on A that the divergence of A is equal to 0, which tells you that k dot q treated as a vector should be 0. So we said that if at any given time you take a particular value of k, this is the given mode k, then in the plane which is orthogonal to it, you have two vectors like this, which you will call E1 and E2. And together your expansion of this A, since it has no component in the direction of k, it can be expanded entirely in terms of E1 and E2, right? So you call E1 and E2 more formally as E k lambda, where lambda is 1 and 2. I could have just put lambda here, it's just a question of notation. So there is a summation over this lambda 1 and 2. And for every value of k, you have to pick ek1 and ek2. Both are vectors, so they carry the vector index alpha. So this is the only complication you have to come to terms with. There are three parameters in this. So one parameter k exists even for a scalar field. So keep that fixed. So you take a particular k. Then for that particular value of k, you have two orthogonal vectors, which we will call the vector ek1. So this is probably better if I write it as ek1, and you have a ek2. These are two separate vectors, which is coded with this lambda value. And since these are vectors, they have components, which is what this notation tells you. Okay, fine. Now by the same token, you also have an identity which will turn out to be extremely useful, that summation over lambda equals 1 to E alpha k lambda E beta k lambda plus k alpha k beta upon k square. This should be equal to delta alpha beta. What does this mean? K alpha upon 1k here is the unit vector in the direction of k. So that is like n alpha, or in your Rustic-Inherited notation, it is like at. Okay, so there is a unit vector in that direction. E alpha and E beta is anyway taken as unit vector. So this is just that if you sum over all the unit vectors with different alpha beta component, you should get Kronecker delta. Now this is obvious, but the simplest proof is that you choose your coordinate system so that this is, let us say, along x-axis, and this is y and this is z. So you have all of them written down like that. Then on the right hand side, unless this x and y are the same, unless alpha and beta are the same, so let's say both of them equal to x. If both of them are equal to x, only this will contribute, that will give you 1. If both of them are equal to y, this will contribute, one of the lambda equals 1 will contribute, and otherwise lambda equals 2 will contribute. And if the indices are different, none of them are going to contribute because they have components only in a particular direction. So once you have proved it in that one coordinate system, since it's a vectorial identity which is invariant under rotation, it remains valid in any other coordinate system. What it tells you, more importantly, is that this particular sum, which we will repeatedly get when we are doing the calculations, can be expressed as delta alpha beta . 1 k alpha k beta upon k square. Okay. Now this is what is called a projection tensor. You should be knowing this, but let me just go over that. If you are given a vector k, there is a tensor you can construct out of it by this definition. This only involves k, and k is just any arbitrary 3 vector. So given any 3 vector, you can construct a tensor like this, which has the property that if you take some arbitrary vector v and you compute v alpha, this projection tensor, which is p alpha beta, you will end up getting the component of v which is orthogonal to the whatever the projection tensor is built up. The projection tensor here is built out of k, so you will get a component which is orthogonal to k. How do you know that? Suppose you multiply it by v alpha. So what do you get here? You get v beta. So it is just the vector itself. Then you are subtracting from it v dot k in the direction of k, right? So if you are given some vector v and you subtract from it the part of v which is along the direction of unit vector k, obviously what you get is the part of v which is perpendicular to k, right? Because you have taken v and subtracted from this part. So diagrammatically, if I have some vector v here and another vector k here, say unit vector k here, so v dot k is going to give you the part of v which is in the direction of k. That if you subtract from v, what you get is the part of v which is perpendicular to k. So this, if you write down tensorially, you will have to have these alphas and betas, and that is what it does. Now very often I will use this with a slight misuse of notation with one up and one down index. Okay. Now here I just want to caution you that when I use it, what is the convention? See, normally if you are doing 3-dimensional vector analysis, this is perfectly correct. Unfortunately, we are using this crazy signature with plus, minus, minus, minus. So k alpha up and k alpha down differ by a sign. Okay? So one can go and put this plus here, but then it doesn't look like a projection tensor, so I won't do that. But when I write it like that, you think of this k square as k alpha up, k alpha down. Okay, so this k square here is interpreted as k alpha up, k alpha down, so it is actually minus k square. That takes care of it. So you just imagine that whatever you have done here, its contraction has to sit here in the denominator. If you have put k alpha, k beta in the same place and you are just squaring and adding, then that is the k square. But this is just a minor issue, but just to make sure the signs are right. Okay, so we have done this much. Now the question is, we have quantized the field. That you have taken this care of this, and AK lambda and its dagger will have the standard commutation rule. So you have number operators. The states of the in the Hilbert space are parameterized by giving number of photons with a momentum k and polarization lambda. Okay. So these integers are raised and lowered by A's and A daggers acting on it, and this is exactly how you do normal radiation theory, semi-classical radiation theory, and all that sort of stuff. But what I stressed last time was that this way of doing things, we first chose the gauge, then we identified the harmonic oscillators, and we quantized the harmonic oscillator. Now in the case of a scalar field, there was no gauge issue. We just took it, we identified the harmonic oscillators and quantized the harmonic oscillators. There was no problem. But in the case of scalar field, I also told you that you could have got this by doing it in a slightly different way, by imposing the commutation rule that phi at t comma x and the canonical momentum conjugate to it at y is equal to I times delta of x minus y. You impose this, then you construct the Hamiltonian operator and then you calculate h commutator phi and h commutator pi, and both of them will give you a field equation which will turn out to be the standard Klein-Gordon equation for phi. Then you can play the same game and get this expansion. We did that also. So the corresponding thing here would have been to take the A alpha as the degrees of freedom at t comma x, and you want to take its canonical conjugate momentum, which would have been like A beta dot at t comma x. It's just like this is phi dot. And impose the commutation rule that this is I delta alpha beta times delta of x minus 1. Different components commute, and in the same component you get this. Okay? This is what you would have done. Now you can immediately see there is a problem. Okay? The problem is that if you take this, yeah.
This should be y, A beta.
Yeah, sorry. This should be y. Yeah. So there is immediately a problem, because if I take the divergence of this, okay, the divergence would be d alpha of A alpha. So on the left hand side I will pick up a d alpha of A alpha. On the right hand side I will have a d alpha of this Dirac-Delta function. Now just as Dirac-Delta function is interpreted as a distribution, d alpha of Dirac-Delta function is a distribution and it is non-zero. Okay? But the left hand side d alpha A alpha is supposed to be identically 0 in this case. So this is 0 commuting with anything will remain 0 even in quantum mechanics. So you have run into a contradiction here, and this cannot work. Therefore, this commutation relation which we are trying to impose is simply wrong. Okay, we shouldn't be using this. Now, but since we had identified the harmonic oscillators and have quantized it, we can now go back and ask what is commutation rule is. What does it give? Okay. So let us try to do that. So this is just a messy computation, not too messy, but it is reasonably messy. But this is something which we have done for scalar field. So I will just try to guide you through as to what we should get. If you have done it with the scalar field, what happened? You started with phi. Then you want to write an expression for phi dot. First of all, this is at the same time, which means I can put t is equal to 0 after taking the derivative. So it's good for you to be able to recognize this pattern so that you will be able to understand why a particular result emerges rather than actually do the algebra. So that is why I want to do it this way. Take phi dot. When you take phi dot, you will pick up a minus I omega here. Right? And you will pick up a plus I omega here. So let us take a minus I omega outside. That means this will come with a minus sign. Then you want to do the commutator. So commutator, you are going to multiply these two together. So you are going to still hang around with 1 minus I omega in one of them. And then these two things will multiply to get a 2 omega. So omega will cancel out. So you have a minus I and a factor 2. Then you just have to do the commutators here. So when you do the commutators, you essentially get A and a minus A dagger. Then you get a dagger and an A, which is with a flip sign. So both of them has a minus sign, so that takes away the minus. I remains, and both commutators are the same. A dagger is just a delta function. So you get an exponential, e to the minus ik x minus y, right? Times an I. Omegas are gone. Since both of them are giving the same factor, you will get a factor 2 which will cancel with the factor 2. So if you have done that computation, which we have, the way the result will emerge is that you will have phi of t x, phi dot at t comma y. You will finally find that there is an I which comes because you differentiated. Then you will have an integral over d3k over 2 pi the whole cube. The 2 omega is gone. 2 went away because there were 2 commutators giving a factor 2. And the omega was hanging around the denominator, but you had one differentiation that cancelled that omega. Okay? So you will have this times e to the plus or minus, it doesn't matter. So I'll just write it as I k dot x minus 1. This is how you end up getting this Dirac delta function. You are with me up to this point. Now let us repeat exactly the same thing for A alpha. When you do that, you will end up getting here, everything will go through. Because root 2 omegas are sitting here and then there is an AK, you will do the differentiation and all that is fine. Except for this E alpha. So you won't have just the integration, you will also have a summation over that E alpha. That is the only difference. So what you will get here is that you will have A alpha t comma x, A beta dot t comma y will turn out to be I integral d3k over 2 pi the whole cube summation over lambda equals 1 to 2 E alpha k lambda E beta k lambda, this quantity times e to the I k. Okay, this is in exact parallel with this, you should work it out. If there is a sign error or something, and towards it can differ in a sign. Okay. Now this is the quantity which you have worked out there. That is why I wrote it down. Okay. So this can be expressed as just the projection tensor. So you have delta alpha beta minus k alpha k beta upon k alpha k alpha. This is what you have. This is k square, of course. Okay. So this is what you get. So this is not a Dirac delta function. So that is why if you had started with a Dirac delta function here, this is wrong and this is the correct expression. So there is a difference between this and this which comes from this. Now let us go back and ask whether the idea works. Suppose I take a d alpha of A alpha. So I take a derivative of this and I get a k alpha here. Now by definition of the projection tensor, this multiplied with k alpha is 0, which you can check. So if I multiply by k alpha, I will get a k beta here. K alpha will cancel out. You get another k beta minus k beta is 0. This way it is nice to write down with a minus sign, so you see that it is cancelling out. Even though I would have put plus and a mod k square here. Okay? So this tells you that what you need to put on the right hand side is what is known as a transverse Dirac delta function. This goes by the name transverse Dirac delta function, just as this is the Dirac delta function. So it is transverse in the sense that if you take the Fourier transform of this is the Dirac delta function. So the Fourier transform of this is 1. The Fourier transform of this transverse Dirac delta function by definition is delta alpha beta minus this quantity. So it is the transverse projector in the case. So what is it numerically? Well, this is not something which you will ever need in your life, I hope so. But it is important for getting some other results. So I will just show you how to do that. Okay. I won't do the full details, but let me just give you how to go about doing this. The idea is very simple. You want to give meaning to this in coordinate space. So let us first of all write this as okay. Let me write this quantity. What we want to compute is what we call the transverse Dirac delta function of x. Instead of x minus y, I can think of it as x, which is by definition integral d3k over 2 pi the whole cube delta alpha beta minus k alpha k beta by k square e to the I k dot x. The first term is trivial. First term is just the ordinary Dirac delta function. Because delta alpha beta out and you integrate, you get this. So I am only interested in this term. So you write this as delta alpha beta, the standard Dirac delta function of x, that is the first term. Then I want to get this, so I put a minus sign. Then this k alpha, k beta can be obtained by differentiating this with respect to, essentially you replace k by a d alpha operator. So k alpha, k beta can be obtained by differentiating with respect to x alpha. Okay? So I have to give meaning only to this. So formally, I will write this, minus signs don't matter because each differentiation will produce an I. And here also I am going to do a derivative that will also give a minus sign, so that doesn't matter. So what you have formally is d alpha d beta upon del square of Dirac delta function. That is, you pull this out and integrate this and write this. So this is all, we are almost there. This is not an issue because I know how to differentiate a quantity with respect to d alpha, but I have to give meaning to this 1 by del square. Okay, and since these are all derivative, they all commute. I can do it in any order. So what I would like to know is how do I give meaning to something like 1 by del square of delta function of x. What is this quantity? So let us say this is some function of x. Then the way you define any inverse operator is by operating with that. So you want del square of f to be delta of x. Right? I have to solve this equation. This is trivial. Poisson equation with a unit charge at the origin. I mean, actually 1 over 4 pi charge at the origin. Okay? So you can compute this, and I think the answer is f of x is minus 1 over 4 pi 1 upon mod x. You can check this factor and the sign. But you have an answer for that. So the del square on that gives you this. So the final answer to this term is just d alpha d beta of 1 upon 4 pi 1 upon modulus of x. Okay? So you can compute it and you will get a number. The main point to notice is that if you take a Dirac delta function, which is a completely localized object, and you act on it with a 1 by del square, you will end up getting a non-local object. This is like saying that if you have a Poisson equation like this, the del square at a given point is related to the charge density at a given point. But the potential at a given point gets contribution from charge elsewhere. So if the charge is non-zero somewhere, then the potential can be non-zero here, even though at this particular point there is no charge. So there is a non-local integration which is involved. It is not important here, but it is going to be important in the next step when we do the next one. Okay. So this is the first point I want you to realize. Okay. Now this result which I have obtained can be now generalized to non-equal terms. What is the commutator at non-equal terms? So what we want to compute next? Let us again go back to scalar field analogy. In the case of a scalar field, we wanted to compute phi at x, phi at y at arbitrary times. We did this, and if I remember right, in our notation, it was given by integral d omega k e to the minus ikx minus e to the ikx. Okay, you can check in your notes. I think something like this is what we have done, where this is let's say x1 and x2, and x is the difference between x and y. Okay, I think some of you would have even done it for the exam. So this is the answer. Now, what do we need? We need to repeat the same calculation for the vector potential. But before we do that, let us look at the importance of this result. When we did it for the scalar field, we made a huge song and dance about it vanishing on space-like separation, right? So that it will commute, etc. So let us ask whether the vector field it vanishes on the space-like separation. To your great surprise, you will find it doesn't. So it is important to realize that it doesn't, and then we will interpret why it doesn't, etc. In this particular case, it is. So you want to compute that quantity. So you are going to look at A beta at some arbitrary point. This is at x and this is at y. And you want to know what this is. Okay. Again, I am not going to redo the calculation. Let us go back and ask how we got this. This is even easier. So you had a phi at some point x and you had a phi at some other point y and you are taking commutator. Right? So when you take the commutator, only a dagger commutator is going to contribute. The other time will have an a dagger a, but it comes with an opposite sign. That is how you get e to the minus ikx and e to the minus ikx. Two factors of root omega will give you an omega, and the a daggers will give you the Dirac delta function to take away one momentum integration. It's completely straightforward. So again, if you do exactly the same thing, what you will get here? Let me write it in fine. Integral, you will have d3k over 2 pi the whole cube. This is essentially coming from this, and then 1 over 2 omega k. This is just this quantity, and you will have these factors, but you will have this in between this quantity, right? So we now know how to handle this. This is going to give you delta alpha beta minus k alpha k beta upon k alpha on e to the this quantity, e to the minus ikx minus e to the ikx. This is what you are left with. So how do you handle this? The rule is again the same. What you do is that you write this as delta alpha beta, or delta alpha beta minus d alpha d beta upon del square, acting on now the quantity which is d omega k e to the minus ikx minus e to the ikx. This is just our old friend, with one convenience that originally when you do this, your omega k is k square plus n square square root. There is a mass. Now we are looking at a massless k, so it is just 1 upon 2 omega k, which is 1 upon 2 mod k. Okay? So these integrals can be done and you can obtain the answer. But we don't need this. But first I want to show that this is not going to vanish outside the light cone. How do you do that? If you do this integral, you are going to end up getting non-zero values inside the light cone, right? So if you look at the light cone structure, this particular quantity which you are going to compute is non-zero here. Then you are doing an 1 by del square. That immediately tells you that it is not going to vanish outside. This is like having a charge here and doing an 1 by del square. And because it is not going to vanish here, you are going to get an answer of that. Okay. Now, just for the for reference, let me tell you how to evaluate that. I won't do it in complete detail. So let us look at this integral. What is it? So the integral which we are interested in is integral over d3k over 2 pi the whole cube 1 upon 2 omega k, which is 1 upon 2 modulus of k. Let me take the first one, which is e to the minus ik, okay, which is modulus of kt plus I k dot x. Everything depends only on modulus of k, so the angular integrations can be done. So what you do is you write this as integral. So d3k you write as 2 pi k square dk sin theta. So you get 2 pi k square dk, so root infinity upon 2 pi the whole cube. Then you have a sin theta d theta, which is d of cos theta, which is standard notation is d mu. Then you have e to the minus I k t. Now k is just a ordinary real variable between 0 and infinity. This is e to the I k r mu coming from this. K r cos theta, that is mu. You guys are familiar with this spherically symmetric integration. So if I do this integral over this, I am going to end up getting 1 upon IKR, then I will get e to the IKR minus e to the minus IKR and the two limits. Right? So you are going to have this k cancelling with this k, and there is only a k there. And oh, I forgot to put this 1 upon 2 omega k. So there is a 2, and then that k also goes here. Right? So you have e to the ik into t minus r here, and there is a t plus r here. And both these cases you can do a decay integration, putting an I epsilon suitably. So you will end up getting an 1 over r minus t plus I epsilon and an 1 over r plus t I epsilon. You can compute that. Then you can obtain the second term. This is all for this e to the minus ikx. This time you can obtain by just changing x to minus x or taking a complex quantity. Okay? So you do the whole calculation, and then you will find that this object in this particular case is proportional to delta of x square theta of x naught. Okay? So what it tells you is that this propagator lives only on the light cone. Delta of x square, I mean now this x square is 4-dimensional x square, it is t square minus r square. So it is on t minus r and t plus r. In fact, if you expand it out, it will just tell you that it is proportional to 1 upon r delta of t minus r plus delta of t plus r. What you are going to do is a inverse del square of this, right? So let us say we call that function some f, then we want del square of that function to give you something like, since there is a Dirac delta function, I can convert it into t, that 1 by r doesn't matter. So let us take this term. Let us assume t is positive, r is always positive, so this cannot contribute. So for positive t, you are going to get something like 1 by t Dirac delta function of t minus r or r minus t. Okay? I hope you are with me. So we came up to this point, then we evaluated this. The only part of that evaluation which I have left out this part for you to do. The only part of the evaluation which I want out of that is that it is going to give you a contribution which is a delta of t minus r and delta of t plus r in standard spherical polar coordinate. You can sort of understand that. What it is telling you is that if you are thinking of an electromagnetic wave propagation or the propagation in electromagnetic context, things will fall as 1 by r, and it will be either on t minus r or t plus r, ingoing waves or outgoing waves. That is what it tells you. So what we want is an 1 by del square of this. So suppose 1 by del square of this quantity is f, then del square of that f is this. Now what is this? This is electrostatics again. This is del square of an electrostatic potential. Okay? In the context, I mean, when you want to think of it electrostatics, you forget t and think of it as r. I mean, it is the same thing because that is just a constant multiplying. Nothing depends. It is an instantaneous propagation, so that doesn't matter. So del square of f del is goes as r minus t means in the normal, now we are doing three-dimensional electrostatics, BSc level electrostatics. At r is equal to t, there is a shell of charge. Okay, so you take r is equal to r naught, there is a shell of charge there, and you want to calculate the potential everywhere. So if you have a shell of charge, then you can say that the potential inside is a constant, spherical shell. Potential inside is a constant, but the potential outside is going to vary with distance. Therefore, when you calculate once you have done that and you calculate the d alpha d beta of that, you are going to end up getting a non-trivial contribution. So for r greater than t, you are going to get a non-trivial contribution. R greater than d, okay, I wrote it down. R greater than t is on the space-like sector of the light cone. At t is equal to 0, it goes all over to the r. Okay? You can in fact think of t is equal to 0 after replacing this by r. Then you have a delta of r is a shell which is collapsing to a origin, and then everywhere outside you are going to have it. So essential point is this is not going to vanish outside the light cone. Okay, so is that a disaster? No, it is not. It is not a disaster because of the same reason that the vector potentials which we are dealing with are not observable quantity. What is observable is the electric and magnetic field. So if electric and magnetic field started having a commutation rule where it does not vanish outside the light cone, we are in trouble. Okay, that will not happen. So let me just try to show you why it does not happen. Suppose we want to calculate it for electric field. So electric field is essentially A alpha dot and A beta dot. So I have to take a dot on both of them. So if I repeat exactly the same calculation, when you take a dot, I am going to bring in something like a omega out, right? So that omega term, there are going to be two of them in both. So I essentially get an omega square kind of a term. That term is going to exactly compensate for this. What you will now end up getting is that it is going to, see, your modulus of k, this came from a k square, so let me write it as k square for a minute. And your omega square is also k square. So this k square will cancel. You will pick up a k square here, right? So the calculation will now give you, instead of this, it is as though you have multiplied by a del square. On this quantity. Now this makes huge amount of difference. If it was 1 by del square is an integral operator, and as I told you, it is not local. The contribution, if there is a charge there, and 1 by del square can produce a field here. But this is a del square operation. So when you go and do this, what you are going to do is to compute this quantity, whatever it is, and then you are going to act on it by a del square and a d alpha d. Now this quantity we know vanishes entirely outside the light cone. Therefore, when you take the derivatives, they will also vanish. So if you compute it for example, electric fields, then you get the result that that quantity is fine. Okay, they vanish outside the light cone. What about magnetic field? You do exactly the same calculation. The only difference is that for magnetic field you have to take curve, but it is again a derivative operation with a k. And you take two of them, so you get 2k's. The moment you have 2k's, this 1 by k square problem goes away. And what is left is something for which things will work out. There is also one more point. I told you that when you do this calculation, the commutator you get for this, the A alpha, A beta, depends on the gauge. And we have used what we call the transverse radiation gauge. You don't want commutators finally for physically relevant quantities to depend on the gauge you have chosen. See, there are, in the case of scalar field, you just have to make sure everything is Lorentz invariant. But when you are working with an electromagnetic field, you have to first show that everything is Lorentz invariant. You also have to show that everything is gauge invariant. And these are sort of linked problems. When you do this Hamiltonian approach where you have separated it into time and space and you have a Hamiltonian which tells you how things evolve, etc., you have already broken Lorentz invariance to some extent. So what remains is making sure gauge invariance holds. And you cannot actually prove gauge invariance without keeping the Lorentz invariance alive. That is why all these problems arise. So in this particular gauge choice, you get this propagator. And when you compute it for the observable quantities like electric and magnetic field, you will get a whole lot of derivatives of the Dirac delta function. They happen to be gauge invariant because the left hand side is gauge invariant and the right hand side should be gauge invariant and it turns out to be gauge invariant. I won't demonstrate that because we don't need it for anything which we are going to do. We are not going to do QED in detail, but this is how the whole structure works. Okay, fine. Now having done all these in radiation gauge, I want to make a few comments in general about other gauges and in particular the concept of a propagator. Now, propagator is just expectation, vacuum expectation value of the time ordered product of the operators, right? We originally had, when we worked with again scalar field, we computed the propagator by computing vacuum expectation value of T of phi at x, phi at x1, phi at x2. This is long back, okay, and we found that this is just x2, x1, and it has a momentum representation which is integral d4t over 2 pi to the power 4 I e to the minus ipx upon p square minus m square plus I square. Right? Now, so this is the quantity we are after. So the propagator in the momentum space is I over plus p square minus m square plus I square, which was a crucial quantity in various things. When we threw in an external source, this is the quantity which came and sat in between. Remember, we did how to add a source to this, then the exponential minus half of j at x, j at x2, j at x1 integrated over x1 at x2 with x2 x1 is what appeared in that. So all these things we will need even for an electromagnetic field if one is working studying processes here. So in particular, I could have put AI and AJ here and could have computed the time ordered product of this and ask what it is. So it has to be a 2-index object, Dij. So if I call this some D of x, in the electromagnetic case it will have 2 indices, I and j, where there will be an AI and AJ, and you want to know what it is. So there are several ways of calculating it, but I would like to introduce one more extra technique which we use here but not in so much a way, but it would be nice to obtain the from, which is what I am going to do next. Now, when we do that, the first result you will find is that for the electromagnetic action which we have written down, the propagator doesn't exist. Okay, so this is yet another surprise. And the propagator doesn't exist again because the theory is gauge invariant. And in order to get a propagator, you have to choose a gauge. And in any given gauge, there is a propagator, and the propagator depends on the gauge. So, but the observed quantities where you use the propagator, multiply it with a current, etc., and compute some transition amplitude, they are all gauge invariant. So, this is what I told you long back. It's a little bit of a mystery, at least to me, that nature arranges matters in such a way that you have to continuously work with a gauge redundant system, like in vector potential. And in non-abelian gauge theories, this is much worse. You have to work with a set of quantities which are not physically observable, and you have all the intermediate states of the calculation where you have to deal with things which are gauge dependent, but final results will all turn out to be gauge dependent. Okay? It's not very clear why this happens, but that is the way it seems, the nature seems to function. So there is probably something interesting here for somebody to work out, but I don't know how to proceed with that. Okay, so let us go back and ask how to get this propagator just from the action. Once we know that, we can repeat it for electromagnetism. So let us start with the action for the scalar field, just to orient ourselves, which was integral d4x, and we had half dA5 minus half m square phi square. Now I want to write this action in momentum space, not in the three-dimensional momentum space, but in four-dimensional momentum space, because I am trying to get this quantity, which is offset, because here p square is not put to equal to m square. So I want to introduce phi of x in the form of a momentum space operator. So that will be integral d4p over 2 pi to the power 4 phi of p in momentum space e to the minus ipx. I think that is the convention we have been following, so that the three-dimensional things will have e to the ipx. Okay? So this is what we have. So we want to plug it in. Now just for convenience, you think of one of them as star. It is a real scalar field, so star does nothing. But here when you take a star, you will get a star and you will get a plus. So the all the Parseval's theorem can be applied and all the momentum integrations can be done trivially. So if you do that, you can see what it will be. All the dAs are equivalent to differentiation, which is minus I PA. But in the other one, you will get a plus I PA. Minus and plus will give you a minus sign, I and I will give you a minus sign, so that will go away. So in all the quadratic expression, I can just replace it by PA. So what I will get here is integral d4p upon 2 pi to the power 4 half p square, okay, half is also outside, half of p square minus m square, and let me write it this way, phi star of p half can be p square minus m square phi of p. Right? This is what this term will go into. Okay? Now we want to write the action exponential I times the action. So if I do exponential I times the action, I want to make sure things are all fine. For that I want to in convergence. So n square should have a negative imaginary epsilon. So one might as well throw it in here. So you put this as p square plus I epsilon phi of p. So I times the action will be I times this and then I times this. This is what you will have. So if I look at the exponential of this quantity, okay, assuming all the signs etc. are right, it is a quadratic in phi of p. I mean, think of it as a summation over all p. So it's a quadratic in phi of p with a quantity in the middle which is I times this quantity. Okay. So the propagator which I have written down there is just reciprocal of this with a minus sign. Okay. If I write this as integral d4p upon 2 pi to the power 4 phi star of p some d of p phi of p, so that the I is put into this keep the I here. So your d of t is I times this, then minus 1 upon d gives you the propagator. Okay, this is what we have found. So this idea always works. Why does it work? Because we know that when we did the functional integral, we started with a quadratic expression like this, then we added a j phi term there, and then we worked out the inverse of this. So the inverse of this matrix, or the determinant of this multiplying with a half factor, etc., the inverse of this matrix which we are computing in the momentum space is just 1 upon this. And this is how we did that. We started with the other expression, then we worked backwards. Okay, fine. Now let us repeat the same analysis for electromagnetism. So you essentially need to invert the object which is sitting there. So the first thing you will notice is that if I am going to do electromagnetism, there will be an index here, L, and some index here, M. So what is going to sit here is going to be a matrix with an ML kind of an index, and I want to invert that. Here it was a pure number, so inversion was just taking the reciprocal. So let us see what happens then. So we again start with action for electromagnetism. That was minus 1 by 4 integral d4x FLM right? This is our old electromagnetic action. So we want to write it in terms of the vector potential. So we first notice that I might as well replace this by dl of AM. There is a dm of AL, but that is going to contribute exactly the same, so I might as well remove this and put a 2 here. Then you expand this out. This is going to be dl of AM minus dm of AL. Okay, this is your action, and you want to rewrite this whole thing in momentum space. So the same rule applies. You are just going to replace everything by all the L's with PL's, because the I and minus I will take care of themselves, and I can put a star on this. Okay. So this will go over to minus half integral d4p upon 2 pi d4. Let us see what this will give. I will have a PL AM in this. Then I will have a PL AM minus PM AL. Now everything is in momentum space. Okay. So let us work that out. This is minus half. Okay, we want to keep all the A factors outside and identify an equivalent of that matrix D there. So let us keep an AM outside. Then I have a PL which I am going to take inside, so that gives me a P square AM minus PM PL AM. Okay. Now, this is the way it looks. Let us make sure of the algebra. PL is P square, and I have a AM outside and an AM inside as it is, and then minus PL PM times a AM. That is what we have. Now, I would like to write it as A something and A something on both sides. So, I am going to first make this AL. So, this AL let me take outside. And in order to get an AM, I had to put a delta ML. So you can see that delta ml on AL will give me an AM, that will give you an AM, right? So this is very nice and clean, except that it's a disaster. So this quantity is what I will call D M L of P. Just as we had a D of P here, we now have a D M L of P because there is a vector index extra on this. So this is quantity. So the propagator is just the inverse of this. So you just have to take this matrix and find its inverse. Now this matrix does not have an inverse. So the matrices which has a zero eigenvalue will have determinant equal to 0, and therefore those matrices will not have an inverse. This matrix has a zero eigenvalue. How do you know that? Because PL is an eigenvector of this matrix with zero eigenvalue. So you take this, multiply it by PL. So if you take D ML PL, you get P square PM minus PM P square, which is 0. So this has a non-trivial eigenvector PL with an eigenvalue equal to 0. So the matrix has a zero eigenvalue, and once the matrix has a zero eigenvalue, it will not have an inverse. So you cannot inverse. So you cannot find the propagator by this. Now why does this happen? The reason it happens is exactly due to gauge invariance. Let us look at this original structure, which was F square. We know it is manifestly gauge invariant. We brought it down to this form, okay, with some matrix here. Now if I make a gauge transformation, gauge transformations in real space involves AL going to AL plus some DL of some function. So in momentum space they involve AL going to AL plus some KL times some function. So if I add to AL something which is KL times an arbitrary function of K, nothing should change. So this object should annihilate when AL has a term which is proportional to K. So it must have this acting on this PL equal to 0. That is a requirement. It's a feature, not a bug. So it has to be there in order to maintain gauge invariant. By the same token, the moment it happens, it will have a zero eigenvalue, therefore its inverse won't exist. So if you want to find propagators in those theories, you have to choose a gauge. Then depending on the gauge, you will get different kind of propagators. Okay? So I don't think I have time to do that part of it now, but I will do it in a minute in the next class. So there are several ways of doing this, and I will discuss two of them. One is a very cheap trick. The idea is to add a mass to it. Okay? The moment you add a mass term to this expression, that is just like you had an m square phi square, you add an m square AL term. That breaks the gauge invariant, because AL term is definitely not gauge invariant, so it breaks the gauge invariant. And then the moment gauge invariance is broken, you will end up getting a matrix which will have a m square term and everything will be fine, and you will end up getting a propagator which is well defined. Then you do a computation with that massive photon, and in the end you take mass going to zero limit, hoping that everything works out. Now I will show you why everything will work out. As long as you are coupling things to conserved currents, the terms which comes from the m square will all vanish. As a result of which things will work out, and that is one way out. Another way out is a very formal technique called Faddeev-Popov method, which again is a very sophisticated method, but it is good to be introduced to it as early as possible. So some of you may go and do field theory at some stage, and in non-abelian gauge theories you need that. So I will just introduce it in this very simple context from path integrals. How is it that this gauge redundancy can be removed in the path integral, and when you remove that, you end up getting a way of adding extra terms to this action, which will break the gauge invariance, and then you can work out the propagator in each one of those cases. Okay, so these two we will do in the next lecture, And after that, I want to do Casimir effect in great detail because I promised that I will do that, and that will again introduce several techniques like regularization techniques and whatnot. So that I will do. That will be the end of this week. Then I will have another 3 plus 3 lectures. Another 3 for some non-perturbative interactions and last 3 for Feynman diagrams and perturbative interactions. So that will be the overall course. So I think that will just get over before your exams begin. Okay. Questions come? Okay. Yeah.